So let me just launch right in. Hopefully you guys remember some of what Giacomo told you after this trip into Fourier decomposition and so forth, because Giacomo basically and I kind of like cut from the same cloth. And so deep learning is huge, but it's in the cloud, right? And the reason why it's so huge is that this backprop learning is powerful. The reason why backprop is powerful is that it can train networks that are deep in space and in time. By deep in space, I mean space is discretized into layers. So you can think of the more layers you go, the deeper the network is in space. And it's also using discrete time steps. So it's deep in time because you can actually train a network with a long memory back in time. That's what backpropagation through time does. And this ability to go deep is what has led to cars driving themselves with some babysitting on your part, but it's getting there. And to apply this learning algorithm, you need a unit's output to be differentiable, right? It has to be a smooth function of its inputs. And so this is a big constraint because, of course, we would like to be not constrained by a lot of these things. In particular, basically, these constraints are limiting the design space. They are very different from the design space in which biology evolved because they cannot take advantage of physical space, which is continuous. They can't take advantage of real time, which is continuous. And they can't take advantage of non-differentiable signals. Spikes are non-differentiable. And so as a hardware designer, we like to take advantage of physical stuff. That's what we build stuff with. And that's what biology works with as well. And so how can we get around these constraints? Well, how do we relax? Part one is basically we can divorce the hardware level abstraction from the functional level abstraction. So we can live with our discrete time, discrete space abstraction, differentiable functions for training, and then find a way of mapping those high-level abstractions or functional level abstractions onto physical ones, right? This is what computers do, right? A computer doesn't actually run, Python or any kind of code that you write. It sort of munches on bits, okay? But you never write down those bits, right? So they've divorced the physical level abstraction. In fact, the first computers, they tried to do multiplication and addition in base 10. And it was a huge thing, right? Until they figured out that binary multiplication table is trivial. Right? It's exclusive OR. Actually, yeah. And so that then made the hardware much simpler. And so we could take a similar approach for the neuromorphic stuff we're building. And there are two existing examples. These are called sort of mapping frameworks. One of them is what you see here in this book that came out in 2003 by Chris Smith and Charlie Anderson. There's somebody here from ABR, Advanced Brain Research, which is Chris's startup. And that's called the Neuroengineering Framework. And another approach, which is more recently developed, is something called the Predictive Coding Framework. And so these are frameworks that allow you to sort of bridge these two levels of abstraction in an automatic way. It's kind of like how you compile your C down to binaries, or you synthesize your chip from Verilog, or your FPGA bits in the lookup tables from Verilog code. And there's another approach which has only recently become possible, is to actually go all the way and train networks that are continuous in time and continuous in space. And there's this paper that just came out, and it won one of the best 5 papers at NIPS, the last NIPS, called Neural ODEs. And another name for these systems, old-fashioned guys like us, we call them dynamical systems. Okay, but the Neural ODE paper allows you to basically train a network in the form of an ordinary differential equation. It could be spatiotemporal. So like the wave equation is a spatiotemporal differential equation. Space is continuous, time is continuous. And this is really, actually, I had a religious experience reading this paper. Okay. It's really, we've been looking for this for like 20 years. Okay, but anyway, this is recent. That's another approach that allows you to actually not compromise at all. And so then once you have these continuous time, continuous space, dynamical systems, then you can sort of map that, synthesize automatically your spiky neural networks to implement them. And what is the payoff? If we're able to do this, what is it in it for us? OK. I think that Giacomo alluded to this. Right now, the thing that we want, where is it that computers have never been? OK, you want to deploy this kind of smarts. Basically, anything that you see that's dumb could be smart. It could be every strut inside a bridge could be smart. There could be a little accelerometer on it. It could be measuring the response to every car that passes by. It could be detecting that, predicting how it's going to respond. If a crack starts developing, it will respond differently. And that little smart device that gets energy from just the vibration of the beam itself will then fire a radio signal. Okay, so these kinds of systems that are deployed way at the edge would harvest energy from the environment, temperature, vibration, light. Will have sensors. It turns out sensing things like sound, acceleration, all that stuff is very cheap. It's microwatts of power. I'm putting my energy harvesting power budget is this red square here. It's about 0.5 milliwatt. To sense acceleration in 3 axes is about 6 microwatts. And then you got to process it. So there's going to be something that's always looking at this signal, predicting how it's going to behave. Basically, that prediction is going to explain 99% of what happens. And when something interesting happens or something unpredicted, it will send an alert via some kind of radio. And of course, radios like Bluetooth energy are like 30 milliwatts, so you can only turn them on about 1% of the time to stay within your energy budget. And the key part of making this happen is these kinds of smarts that can basically predict what's happening in the environment with these naturally occurring signals. And the idea is that the most efficient way to do this, right now people are saying they can do this for milliwatts, but digitally, but you want to get down to microwatts or even fractions of a microwatt, basically the kind of energy that a pacemaker uses inside the heart, so that you only have to do surgery every 10 years to replace the battery. OK, that is like 70 microwatts. So basically this is what is out there for us. I don't think that von Neumann and Turing are going to go here. And they're going to be doing what they're doing. But we could make everything around us smart with huge implications for health, energy, and the environment. And so how do you minimize energy? OK, so then I'm going back up now to try and sort of start again from a high level, because this is what everybody is familiar with. This is your matrix multiply. You take an activity in one layer, multiply by that matrix, you get the activity in the next layer. It's fully connected. We've had all kinds of schemes, very clever schemes to make this more efficient. But normally, the number of operations you're doing is if you actually are smart, the number of active neurons in this layer, or units in this layer, times the number of connections each guy is connected to. And this number here, if you are smart, can be some fraction p active of the actual number in that layer. And this number here, if you're smart, can be some fraction of the actual number of connections, right? And so you want to basically exploit these two things to reduce the amount of compute. And it also reduces the amount of communication, because each time a thing's active or you have to read a weight from memory and all that, those things track each other. And so this p-active part is what you would call temporal sparsity, where if you're in the discrete time, time steps and quantized digital levels, your activity on these units look like this. And these two guys are at 0, so they are not active. And you don't need to update those connections. But most of the time you do, because you're hardwired in a crossbar, or you've got a full TPU with 2v6 by 2v6 multiply accumulates. It does it anyway. But if you design you could design your architecture to take advantage of that. And that will give you that's how you take advantage of that. But you can actually make things even temporarily more sparse by taking advantage of spikes, because spikes are already designed. When you use spikes, you design your architecture to be event-driven. It only does something when a spike occurs. And then you can really push on this temporal sparsity with spikes. So I see that as the advantage of spikes. What about the spatial sparsity? You want to have sparse connections. People do this. They train the network, and they find out that they can compress the weights. It's not full rank, or they can make it mostly zeros and things like that. And so that's another thing you can take advantage of. And one way that we are taking advantage of it is by basically combining analog with digital. So this is what I call analog convolving. Basically, we are delivering the digital signals that we've weighted to some sparse points, and then we are relying on some pre-wired kernel, like a convolutional kernel, to distribute those signals to all the neurons. And this is sort of like the dendritic tree of a neuron. Convolution was developed to explain how a cable actually propagates a signal. Okay, that's yeah. And so that kind of thing can actually, help you push down on the sparsify your connectivity. This is the main thing that I'm going to focus on for the rest of the talk. And I like to summarize sort of the way that I look at what the brain is teaching us as, when you design a computer, you have a choice of how you represent the signal for computation, whether analog or digital. And you also have a choice for how you represent the signal for communication, analog or digital. We went from this analog quadrant before World War II to this digital quadrant. After World War II, you can blame Steve Febers at Manchester for this. And over here, the ENIAC at University of Pennsylvania, that's this picture. And the brain sits in this quadrant over here, where it uses analog for computation and digital for communication, if you simplify it extremely. But in actual fact, dendrites are analog, so it actually uses analog to communicate as well. So it sort of overlaps these two. It has this mixed signal for communication. But once all those inputs come in to generate the output, that's all analog inside the neuron itself. And so what is, the big deal about analog? Okay, so I kind of been talking about, I've been working in this field for like 3 decades. And, I rely on my students to come up with better ways of communicating this idea, because it seems so obvious to me. And so this is some folk, came up with this example where he took your iPhone. It's got a 4.3 billion transistor processor in it, and it's got a 10 watt-hour battery. It runs for 8 hours. Then you plug it in the evening when you go to sleep. And if you take that amount of power, how much current you can drain over it takes, and you divide that current among these 4.3 billion transistors, it turns out that each of those transistors can, for the 8 hours, pass on the order of something like 1/10 of a nanoamp. Okay, so this is current, and that's how much, on average, each of these transistors are passing. They are not analog, they are switching. Okay, or they are sitting in the memory and they are leaking and so forth. But that's what it amounts to, draining that battery. Now, what I've shown here is the gate voltage applied to a transistor. And as you increase that from 0 to 1 volt, you go from the subthreshold region to the above threshold region. The threshold is around this level here. The current goes exponentially. This is a log scale, and then it becomes quadratic, increases quadratically. And you can see, actually, if we operated these 4.3 billion transistors down here with a picomp of current each, we'll go for 100 days on your iPhone battery. If we operated them with like 10 femtoamps each, we'll go for 27 years on your iPhone battery. You could have something sitting there computing for 27 years with all these 4.3 billion transistors, right? I mean, how much is it an electron per second? It's still way more. It's like an electron per second is 10 to the minus 19 or something, right? So that's still a lot of current. But anyway, yeah, so this is, what we could be doing with all these transistors. But why aren't we doing it? Why do you have to plug in your phone every day? And why, actually, most of the transistors in your phone don't compute for you. They are just leaking because they are in memory. Because there's some huge challenges with building analog stuff. Okay, it's not easy. Okay. So again, I also find that I have to communicate things in a sort of emotional way to people. Otherwise, they just look at these numbers and it doesn't register. And so back in 2013, this is actually some folk that came up with the iPhone analogy. And this is Samir Menon and Alex Necker. Sam and Alex went on to sort of tackle these horrible analog problems. And these are two undergrads that they work with to set up this robot demo. So yeah, Samir basically was co-advised with Osama Khatib, and we took his robot control algorithms, and we implemented them on NeuroGrid, which is sitting over here. And they were very excited. They worked really hard. They got this demo to work. They drove it, a bunch of computers, a bunch of robots, to Tahoe for the NIPS workshop. Well, they had a demo at NIPS. And so they got everything set up on the table. You know, you basically sit here, you move this mouse around, and the computer will send the vector from the end effector of the robot to where you put the mouse. And those three numbers would go to NeuroGrid. NeuroGrid is also getting the joint angles of these robots. They are 3 degrees of freedom robots that through the computer, which is animating the robot to correspond to what's happening here. And it takes those 6 numbers and it computes the torques that have to be driven to the 3 motors to move to that location. And so you move your mouse around and the robot will move. And it was all done with these spiking neurons, mixed analog digital stuff. So they got it all working. They set it up. People started showing up for the demo. People were like, oh, robot, cool, what's happening? It's moving. And so as people crowded around, the temperature changed. It increased. The analog transistor started passing more current. The robot started moving around faster. And then it started oscillating, and people were like, wow, that's exciting. More people came. It started moving around even faster. So yeah, it's a real problem. This is why we build stuff. We know what the important problem is. We would have been working on something completely different. And so it's not, that has to happen for you to figure it out, but it's not like we don't understand this. Like the device guys in here, we know it. It's temperature dependent. So sorry for the fade. My resolution is too high for the projector. But anyway, so this is again the transistor characteristic. This is the gate voltage. This is the drain source current. But what I've done is that I've repeated the simulation for 1,000 transistors that are identical size. And I get this spread here, which corresponds to the variability, basically the manufacturing tolerance of the manufacturing process, the tolerance of the manufacturing process. So the guys at Albany do a heroic effort, but they can't place each atom one at a time. They'll never make any money, so they spray them on there. And that's what you get. So there's some tolerance. And so if you zoom in to this part in the subthreshold region, you'll find out that this fuzz, this is 2 decades from here to here. The amount of current that these 1,000 transistors are passing spans a decade, even though they're getting the same gate voltage. Most people build analog stuff up here where they are passing a lot more current. Your iPhone would just last for like less than an hour, maybe 10 minutes. And if all the transistors were operating up here, and here you only have maybe from 3.5 to 4.5 or something, 25% variation in the current for the same voltage. So we are down here where we are exponentially sensitive to these, what I call threshold voltage mismatch. And it's about a decade, so that's huge variability. And so when you fabricate one of these transistors, you get a whole bunch of curves like this. I'll explain later why these guys are going this way and those guys are going that way if I have time. And but these are a bunch of curves measured from BrainDrop at 26 degrees Celsius. They have different thresholds. They have different gains. There's a lot of variability. That's what happens with the variability in analog transistors, because we make them small. We pack as many as possible in there. And not only that, we are temperature sensitive. So if you took just the same transistor and you swept the temperature over 50 degrees Celsius, you find out down here it changes by almost 3 decades. That's 3 decades of current here. And then so the variability is on the order of, with temperature over 50 degrees Celsius range, about 1.5 to 3 decades. And so it turned out that when we got NeuroGrid back in the lab and we measured some tuning curves, we put it in an oven, we swept the tuning curves, we could decode temperature from NeuroGrid neurons with 0.2 degrees Celsius accuracy. Okay. So, yeah, but that was over a 2 degrees Celsius range because it was much worse than this. This is the transistor level. And it's much worse than BrainDrop. But in BrainDrop, because of all this experience that we had, we came up with a better design. And here is sort of the typical variation. You get over 40 degrees Celsius is 38 degrees Celsius. You can see this neuron here turns on when it's cold over here. And when you increase the temperature by 40 degrees, it has a higher threshold and lower firing rate. Actually, you get all kinds of different patterns of response. And some guys that just get lucky don't change much. And so how do you compute with these kinds of devices? The way that we were doing it for the robot demo is that we pick some function, typically some sinusoid and cosine and things like that, that describe the Jacobian for the, from torque to force. And with that function is here, and then we have a bunch of tuning curves, and we want to find a weighted sum of those tuning curves, which is the plots I was showing you before, the neurogrid neurons, how each one responds. That will give us a linearly weighted combination of those tuning curves. The neuron's responses gives us the function that we want. And so we basically sweep the input. This would be like the 3 force coordinates or whatever we want. X, we sweep that. We measure the response of neuron 1, neuron 2, neuron 3. We put that all into this A matrix. And then we multiply it by, if there are n neurons, we have n weights. They are called decoding weights. And we are trying to solve this problem to get this function of x that we want to use to control the robot. And you do that using the pseudo-inverse, which came up before. It's like machine learning 101. And this is just showing you a sinusoidal response. We are feeding this range of input into neurogrid neurons, and we're only using like 3 neurons here to approximate the sinusoid, but as we increase the number of neurons, we can approximate the sinusoid really well. And also the fuzz, the amount of noise we have. The fuzz is how much noisy those curves are. That goes down as we add more neurons as well. And so how do we deal with temperature? We do the same thing, but now we measure the A matrix at all these different temperatures, and we solve for a set of decoders that if I take those decoders, I multiply by this matrix, I get that function. I multiply the next temperature matrix, I get the same function, and all that. So I solve for a set of decoders that are in the null space of the temperature variation. And it works. So now at 40 degrees Celsius from BrainDrop, 256 BrainDrop neurons, I can basically decode temperature invariant this function. If it's quadratic, I can still do pretty good. As the function gets more complicated, I start seeing the thermal variation, like you see here. There's the same amount of thermal variation here, but it's very tight. Because, yeah, so you could increase the number of neurons and you could get that down as well. And so these techniques are basically what the mapping framework that Chris Eliasmith proposed basically formalized these techniques, where you start out with a population of spiking neurons, and you basically apply weights. You treat the spikes as impulses with unit area, and you apply weights of them, which scales the area by the weight. So each connection here has a different weight, and if it's negative, we flip the sign. We just carry a minus sign along with the spike. And then we basically just merge these spike trains together. That corresponds to a decoded function of f, represented as scaled spikes. And you can do it again to apply a transform, any matrix linear transformation from this decoded quantity to another decoded quantity. And then you encode. You give each of these neurons here some preferred direction in this 2-dimensional space. So this guy likes a lot of this, none of that. This guy likes about equal amounts of this and that. That will correspond to this direction in 2-dimensional space versus that direction or that direction. And so whatever dimensionality your problem is, you assign your encoders there. And then at the end here, you go through a synapse, but this is a dynamic synapse. So it converts those spikes into these current waveforms that drive the neurons to spike, and you're back here. And so this, and then of course you solve for these decoding weights using that pseudo-inverse approach that I described. Okay, and so we made some modifications to implement this in hardware, mostly driven by the fact that, because we're going to solve for these decoding weights offline, we want to apply them exactly the way that we solve for them. So we have to be precise in the way we apply the weighting. So we do this digitally, but then we then do this part here, the encoders and the filtering in analog. Okay, and so I hope the optical. Are you following?
What's that?
Are you following this stuff?
I am, yeah.
Yeah, okay, good. Yeah, exactly. So what we do in BrainDrop, which is what the chip is called, is we basically replace the merging operation that happens here with what we call accumulative thinning. It's a way of basically letting, if you want to apply a weight of 1/3, then you let every third spike through on that channel, but you don't change the area. And so basically what it does is it thins, but then it restores. So these are scaled by the area. It adds up area of these guys until it gets digitally, until it gets to 1, then it lets a spike out. Okay? And if it's negative, it goes the other direction. If it accumulates -1, it will let the negative spike out. And you can see this is actually quite efficient at sparsifying in time. These 9 spikes actually only produced 2 spikes because of the way they were weighted. And then we take those and we find out not to all the neurons in this layer, but to these few synaptic filters, and then we use the analog convolution to then mix different weighted combinations of these 2 signals and deliver them to each neuron. That gives us these encoding directions. And we can do it in 3D. We can do whatever dimensionality that you want. We don't have time to get into it. So the architecture looks like this, where we start up with a layer of neurons, and they spike, and we multiplex all those spikes out using address events like Giacomo described. And then we basically go into a on-chip memory. We're using SRAM in 28, but we could use something more dense. And we pull out the decoding weights for that guy. These would be the decoding weights. And then we pull out the state of these accumulators, they're called, and we update them with the weights that we pulled out, and we put them back. And then if an accumulator trips, we generate a new thing. We call it a tag, because we use indirection to then access a particular location in this memory here. And so then that location there tells us basically whether we should go and do a transform, or we should go back and hit some synapses here and go back into the next pool. And so we can divide up this population into logically many pools that we want, and we can connect them arbitrarily by using these tags and this addressing mechanism. And in this case, we wanted to do a transform, so we went back here. We applied these guys to another set of accumulators, and then we came back out. And then now this lookup table told us that, OK, you're going to go back and hit some synapses. So we come back in here, and we hit those guys, and then we hit the analog currents get delivered through this. It's implemented with transistor, this sort of resistive network implemented with transistors. And so that's what the chip looks like, is the size of your credit card. That's what the die looks like sitting inside this package. You blow it up, it's about 2 by 2 millimeters and 28 FDSOI. I think the same process Giacomo is using. And this is our SRAM for decoding weights and transforms. And these are sort of other lookup tables for tags and things like that. And these are neurons, 64 by 64, 2D array of those neurons, 4096, intermingled with the synapses, filters, and so forth. And then the routing for taking spikes in and out of those neuron arrays. And the way we program it, this was done in collaboration with Chris Erasmus' group. They developed this really nice software environment called Nango. You write down the system you're trying to build in terms of these functions you want to compute, or even differential equations that that relate one input to output. And you write that up, and that basically then gets converted to a network of pools of neurons, and they are interconnected so that A then gets fed into there and so forth. But each of these equations corresponds to a pool of neurons, and actually you describe it in Python, and you can do it interactively and play with it. And we basically design a chip to sit like a back end. Either you can run this code on the computer, or you can actually run it on the chip itself. And this is an example of a system that we've implemented on there. I'm sort of running low on time, but this is what's really, the pseudo-inverse and all this stuff, function approximation, all this stuff you guys have seen before. But this is really what's unique about the NEF. You can implement dynamical systems. And then I have to talk to my optical friend here. I'm going to do that optically. but if this little mote or this little IoT device is sitting there and trying to predict what's happening in the world, it's very important that it can learn dynamics. And the way that happens in NEF is basically you do the encode. Like I said, these are the synaptic filters feeding currents into these neurons with some random mix of weights. And then the isomers then spike, and then you weight them. You do the decode. So I'm just going back to your classic NEF. But what I didn't point out is that if you recurrently connect this back to form a recurrent network, then you've implemented a dynamical system. In particular, the dynamical system this thing implements is this tau sin, which is tau is the time constant of the synapses, and x is just this vector of signals, continuous signals that your network state is described as. And these are the weights you're applying to your spikes, and this is your external input. And basically, you can compute a set of decoding weights to approximate any nonlinear dynamical system that you want. For example, if you want to approximate this nonlinear dynamical system, so some arbitrary function of x plus some input gives you with some arbitrary time constant. This could be multidimensional as well. you basically solve for decoders that approximate a scaled version of this plus x. And if you plug that into here, the whole thing collapses to that. And so, of course, you have to scale the input as well. So you can implement arbitrary dynamical systems, and we've done an example like this. This is actually running on BrainDrop, and that's my last technical slide, where Chris's student, Aaron Walker, came up with this way to model an efficient way of implementing what's called a delay network. You can think of it as a reservoir. So what a reservoir, we heard about some of that this morning, is trying to sort of keep information over time and then allow you to then mix different inputs that came in different times non-linearly so that you can detect some particular pattern, like a particular word that was spoken. And so basically you can just write down a dynamical system for this, right? You want to basically have a multidimensional dynamical system such that x dot is some matrix A times x weighted by the input, but then you want to be able to, from this state, be able to apply another matrix and decode out not what just came in at this time, but something that came in at some point earlier in time. And since we're engineering this from first principles, we can derive the optimal way to do this. And within some time window, we can recall anything that we want from that state. And so, and this is what you're showing here. So different colors, fading, deeper colors correspond to recalling this signal further and further back into the past. Okay. And this is in a three-dimensional version. If you make it higher dimensional, you can even get more history or more bandwidth. And this is showing that the BrainDrop is actually approximating quite accurately what's happening in terms of the state that it's capturing in X compared to the theory. And so I just have performance slides here now, but I can skip those. We've measured energy per operation of each operation and so forth. It's for your hardcore chip guys. And this is how the things scale. But basically, the energy per equivalent synaptic operation we get depends on the signal-to-noise ratio that we desire. And basically, and also the dimensionality, basically how many neurons we use per dimension. So if you have a d-dimensional system and we're using n neurons, then n over d is the neurons per dimension. And so as you increase that, we are more efficient because basically we are spatially specifying by this factor of d over n. And as you increase SNR, we are also more efficient energy. We are using lower energy per synaptic operation because we are actually temporarily thinning, temporarily specifying by 1 over the SNR. I don't have time to explain why it comes out that way, but basically, so BrainDrop sits here for a typical about SNR of about 20. We are getting about 380 femtojoules per synaptic operation, whereas True North and Loihi at about 25 picojoules per synaptic operation. And so we like to pride ourselves as the first guys who beat the GPU, because the Tesla GPU right now is at 2.5 picojoules per floating point operation. So yeah, so that's just energy per synaptic operation. But as everybody will tell you, what we really want to know is for a given task, how much energy do we use, and how does that scale with the task complexity? And we are hoping that even though we lose here, we might scale better or whatever, but there's a question mark here. We still have to do that part of the thing. We focused on hardware design right now, but the energy you're going to use for a given task is a combination of whatever network is required to solve that task and whatever energy you take to execute that network, right? And we're assuming we do the same network as the other guys, but this is going to change. As you put more constraints, temporally specifying and spatially specifying, it may impact the size of the network adversely. So we still have to sort of evaluate that whole stack all the way to the application energy. But so far, we basically, what I've talked about is we focus mostly on specifying this. I think we can still specify in time more, but that's the next project. Okay? So thanks, everybody.
Thank you, Kwabena.